So today, it's my pleasure to welcome Joshua Batson from Anthropic. So he'll be talking about on the biology of a large language model, which should be a very interesting talk. So Josh leads the circuits effort of the Anthropic mechanistic interpretability team. Before Anthropic, he worked on viral genomics and computational microscopy at the Chan Zuckerberg Biohub. And his academic training is in pure mathematics, which is very cool and impressive. And just another thing, which is some more recordings for this quarter have released, like Karina and Div's talks. So feel free to check those out on our YouTube playlist. And for the folks on Zoom, feel free to ask questions either on the Zoom or the Slido with the code CS25. And without further ado, I'll hand it off to Josh.
Thank you. Clap, come on, we're getting started. Okay. It's a pleasure to be here. It's crazy to me that there is a class on transformers now, which I think, were invented rather recently. We've got like an hour for the class, I guess, and then like 15, 20 minutes for questions. Feel free to just like interrupt me with questions. Like as he said, like my training's in pure mathematics and like people just interrupt each other all the time very rudely, and it's totally fine. And so if I want to just cut you off and move on to something, I will. But this can kind of be as interactive as you guys would like it to be, and that's true for the people on Zoom too. Okay, so this talk is titled "On the Biology of a Large Language Model," which is also the title of a paper, which is what we call our like 100-page interactive blog posts that went out a few weeks ago. And if you're here, you probably know something about large language models. The biology word is like, was our sort of choice here, and maybe you should contrast it to like, a series of papers called On the Physics of Large Language Models, where you're sort of thinking of them as like dynamical systems over the course of training. But we sort of think of, interpretability being in relationship to neural networks as, which are trained by gradient descent, right? As biology is to living systems that are developed through evolution. So you have some process that gives rise to complexity, and you can just study the objects that are produced for like how they do the kind of miraculous things that they do. So models do lots of cool things. I don't need to tell you guys this. This is an example, I don't know when it's from now, maybe 6 months ago, which is like 10 years in AI time. But I quite enjoyed this. This was just somebody who was working on natural language processing for Circassian, which is like a very low resource language. Not many people speak it. There's not many documents. And he'd been sort of tracking the state of the art in NLP for many years, like, using the best models at the time to try to like just help translate into this language, translate from this language, help preserve it. Tried it with a version of Claude where I think this was probably Sonnet 3.5, where he just shoved this master list of Russian circadian translations into the context window. So just like painstakingly gathered over years, rather than train a model, just put it in the context window and then just ask the model to do like other translations. And it could not only translate it successfully, but also kind of like break down the grammar. Right, and so just in-context learning with these models was sort of enough to beat the state of the art for the NLP-specific models that he'd been working on for a while. So, like, that's cool, would be my summary of that. But models are also weird. So this was also Claude, and someone asked it, what day is tomorrow on Leap Day? And it's just like got in a big fight. If today is February 29th, 2024, then tomorrow would be March 1st. However, 2024 is not a leap year, which is untrue. So February 29th is not a valid date in the Gregorian calendar. Okay, now it starts around the rules. Following this, 2000 was a leap year. 2100 will not be. Like, fine. And then it says the next leap year after 2024 will be 2028. Which is true. And then, so if we assume you meant February 28th, 2024, the last valid date in February. Then it gives it, it's just like, what is going on, right? There's like some smorgasbord of like correct recollection of facts, correct reasoning from the facts, and then like disregarding them out of consistency with this like initial, it's just pretty weird for it to be leap day. It's like, that's odd, right? I mean, if a person were doing this, you would wonder like what was in the brownies they had consumed. There's just this like, now children are sort of like this, so maybe that's an interesting topic. And then I just love this. AI art will make designers obsolete, AI accepting the job. And it's got so many fingers. This is like now out of date, right? Like people have figured out how to keep the finger count down to at most 5 per hand. You know, the new ChatGPT model, right, can do like extremely realistic people, and they all have 5 fingers now. But like that wasn't exactly solved by figuring out like why are there so many fingers on these? You know, just sort of like other methods got through it. But like presumably you kind of bat down some of this weirdness, and now it's just the weirdness is more sophisticated. So as the models get better, you need to get better at understanding just where like the craziness has sort of gone. So as the frontier moves forward, like maybe it's not 5 fingers, but there might be subtly other things that are wrong. And when I think about interpretability, which is sort of like, what did the model learn exactly? How is it represented inside the model? How does it manifest in behaviors? I am sort of thinking ahead to when, you know, most of the simple interactions seem to go well. And then it's like, are these going well because fundamentally the model learned something like deep and true, or because you've managed to kind of beat this down like the finger problem, but like if you went out to the edge of the model's capabilities, it would all be 7 fingers again, but you can't tell. And also because it seems pretty reliable, you've delegated a lot of decision making and trust to these models, and it's in the corner you can no longer verify where things get weird. So for that reason, we kind of want to understand, you know, what's going on with these capabilities. All right, so this will be a bit of a review at the beginning of like why models are hard to understand, some strategies for picking them apart, and then 3 main lessons I think we've learned about how models work inside that like aren't obvious from a black box way of engaging with them. So here are sort of three statements that are like somewhere between myths or things that are out of date, or like true if you interpret them in one way philosophically, but missing the point. And so these statements are that models just pattern match to similar training data examples, that they use only like shallow and simple heuristics and reasoning, and that they just kind of work one word at a time, you know, just kind of like gutting out the next thing in some like eruption of spontaneity. And I think, you know, we find that models learn and can compose pretty abstract representations inside, that they perform rather complex and often heavily parallel computations. It's not serial, so they're doing a bunch of things at once at the same time. And also that they plan many tokens into the future. So even though they say one word at a time, they're often thinking ahead quite far to be able to make something coherent, which will work for that. Okay. This is probably a review for this class, but we made these nice slides, and I think it's nice to go through anyway. So you have a chat bot, which is, hello, how can I assist you? As an answer, how does this actually happen, right? You know, it is saying one word at a time by just predicting the next word. So how goes through Claude and predicts can, and how can goes to I, and how can I goes to assist, and how can I assist goes to you. So you can reduce the problem to the computation that gives you the next word. And that is a neural network. Here I've drawn like a fully connected network. To turn language into language, passing through numbers, you have to turn things into vectors first. So there's an embedding. So every word or token in the vocabulary has an embedding, which is a list of numbers or a vector. Morally speaking, you basically just concatenate those together and run them through, you know, a massive, you know, neural network with a lot of weights. Out comes a score for every word in the vocabulary, and the model says the highest scoring word, modulo some temperature to introduce randomness. Transformer architectures are more complex. There's these residual connections, alternating attention and MLP blocks, which you could think of as like baking in a really strong priors into a massive MLP. But in some sense, that's just about efficiency. So a metaphor we found useful, which is also biological, is that language models should be thought of as grown, not built. Like you kind of start with this randomly initialized thing in architecture, which is like a scaffold. You like give it some data. Maybe that's like a nutrients, and then the loss is like the sun, and it grows towards that. And so you get this kind of organic thing, which has been made by the end of it. And you know, but the way that it grew, you don't really have any access to. The scaffold you have access to. But that's like looking at a model at a nit, which tends not to be that interesting. Okay, so. Of course, like we have the models, and so there is a tautological answer to what are they doing, which I already told you, which is they turn the words into numbers. They do a bunch of matmols. They apply like simple functions. It's just math all the way through, and then you get something out, and it's like, that's it. That's what the model does. And I think that's an unsatisfying answer because you can't reason about it, right? Like that answer to how do models work like doesn't tell you about what behaviors they should or shouldn't be able to do or kind of any of those things. So the first thing you might hope is that the neurons inside the neural network might have interpretable roles. You know, people were hoping this going back to the first networks in the 80s. There was a bit of a resurgence in deep learning, a kind of small one. Chris Olah, who leads the team at Anthropic, got really into this 10 years ago. You just like look at a neuron and you ask, when does this fire? For what inputs is this neuron active? And then you just sort of see like, do those form a coherent class, right? This is the car detector neuron in a vision model, or this is the eye detector, or this is like the edge detector if it's early in the model, you know. They found like the Donald Trump neuron in a clip model. For example. But it turns out that in language models, when you do this, you just say, which sentences cause this neuron to activate? The answer doesn't make that much sense. So here's a visualization of a bunch of example text for which a neuron in a model activates, and there's just a lot of stuff. There's like code and some Chinese and some math and hemlock for Socrates. It's not especially clear. And like, of course, there's no reason it would need to be, right? Like it's just learned a function. And so asking for a neuron to be interpretable is like a bit of a Hail Mary. And it's pretty cool that like works sometimes, but it's like not particularly systematic. So there's a prior from neuroscience is that like maybe while there's a whole bunch of neurons going on or something, that at any given moment, maybe the model's like not thinking of that many things at once. Maybe there's some sparsity here where if there were a map of the concepts the model is using or the subroutines it's using or something, that on any given token, it's only using a few at a time. And that's just, you know, maybe a slightly better guess than maybe the neurons are interpretable. It's like not necessarily a great prior, but it's something you can work with. And so you can fit linear combinations of neurons such that each activation vector is a sparse combination of these dictionary elements. This is called dictionary learning, classical ML, and we just did it. So you just like gather a bunch of activations from the model when you put through a trillion texts or something, and then you take those vectors, you look for dictionaries, and then you look at when are those dictionary components active, and lo and behold, it's way better. So, you know, we had a paper last year which was just like, here's a bunch of them where we fit about 30 million features on Claude 3 Sonnet on the middle layer of the model. So you just say, you know, what are the atoms of computation or representation inside that model? This was one of my favorites where this linear combination is present, or it's like a dot product with a vector is large, when the input is about the Golden Gate Bridge. And that is true if it is like an explicit mention of the Golden Gate Bridge in English on the left. Also true if it's translated into another language. Also true if it's an image of the Golden Gate Bridge. Also true, it turns out, if it's an indirect mention. So you're like, I was driving from San Francisco to Marin, right? Which, you know, you cross the bridge to do, and the same feature is active there, right? So it's like some relatively general concept, also in like San Francisco landmarks, et cetera. So these combinations of neurons are interpretable. We were happy with this. There's things that are more abstract. notions of inner conflict. There was a feature for like bugs in code that like fired on kind of small bugs like division by zero or typos or something. In many different programming languages, if you suppressed it, the model would act like there wasn't a bug. If you activated it, the model would give you a traceback as if there were a bug. And so it sort of had this general properties. But there was something very unsatisfying about this, which is like, how does it know it's the Golden Gate Bridge? And so what? What does it do with that information? Right? So even if you manage to like piece apart the representations, that's just a cross section. It kind of doesn't give you the why and the how. It just gives you the what. And so we wanted to find ways of connecting these features together. So you start from the input words, and you're going to process these to higher order representations, and eventually it'll say something, and trying to trace that through. Through optimization. So very concretely, you have a matrix, which is like you take 1 billion examples and of activation vectors, and then you've got D-model here. That's a matrix. And you try to factorize that matrix into a product of a fixed dictionary of atoms times a sparse matrix of which atoms are present in which example. And you just have an objective function, which is this should reconstruct the data and some L1 penalty to encourage sparsity. It's a joint optimization problem. Yeah, that's right. That's right. We tried being clever about this. There's like a beautiful, rich literature on dictionary learning. But after a few months of that, the bitter lesson got us. And it turned out that you could just use like a 1-layer sparse autoencoder, which you can like put in Torch and then just like train on your GPUs. And like that scaling was more important than being clever yet again. So that's what it is. It's a sort of sparse autoencoder. All right. So here's a prompt. Okay, so the capital of the state containing Dallas is Austin. This is true. That's because the state containing Dallas is Texas. Good. Did the model do that? Was it like Texas? So Austin? Or is it like, I don't know, it seemed a lot of training data. Like, was this just in it? And it's just like reciting the answer. There's a lot of eval contamination, like a lot of MLU made it into people's training sets, so you get high scores. Well, just knew the answer to that literally because it had seen it. So did it literally see this before, or is it kind of thinking Texas like you did? It's thinking about Texas. So I'll tell you, this is like a cartoon, and we can slowly through this like pick, break away these abstractions to like literally what we did. But I'll sort of start by saying that you should think of each of these as sort of bundles of features, which are, again, atoms we sort of learned through an optimization process. We label the role of each feature by looking at when it's active and trying to see if we can describe kind of in language, what that feature is doing. And then the connections between them are actually direct causal connections as the model, processes this in a forward pass. And so what we do is we break apart the model into pieces. We ask, which pieces are active? Can we interpret them separately? And then how does it flow? And so in this case, we found, a bunch of features related to capitals, a bunch related to states in the abstract, a bunch related to Dallas. We found some features that were like, you can think of as like motor neurons. They make the model do something. In this case, they make it say the name of a capital. Like they make it say a bunch of state capitals or country capitals or something. So that's a start. But also it has to get it right. And so, there's some mapping from Dallas into Texas. And there's a pile of features there. Some are like, discussions of like Texas politics. Some are like phrases like everything's bigger in Texas. And once you have Texas in a capital, you get saying Austin in particular. And, if you're saying a state capital and also you're saying Austin, what you get is like Austin coming out. There's some interesting straight lines though, so like Texas also feeds into Austin directly, right? If you're thinking about Texas, you might just be thinking about Austin. And so, I'll get into more of how we build this. But this gives you a sort of a picture in terms of these atoms or dictionary elements we've learned And you might want to check that they make sense. So then you can do interventions on the model, deleting pieces of this, like in neuroscience, these would be ablations of neurons or something. And then you see if the output of the model changes as you would expect.
Someone on Zoom asked, words like Dallas and Austin frequently appear together in internet text, suggesting simple statistical correlations. So is this a way of overcomplicating things?
I think that people have found that transformers have outperformed back of N for most tasks. So, Houston also occurs, with Dallas in the training data, and the model doesn't say Houston, so it must be using the capital and Dallas. In this case, I think you could say, maybe if you just had capital and Dallas, then it would say Austin, and that's actually true, I think. Some of this edges were pretty weak, and it turns out you could just say the capital, make something ungrammatical, just like, the capital of Dallas is, and it will say Austin. And that's an interesting thing where I think you look at the graph and this edge is weak, and it indicates that actually maybe it is just like if you have capital and Dallas in proximity, you might get Austin, which is then causally true. Yes.
A layer and a layer. The structure of that, the capital is a neural network, a layer and a buffer layer.
Yeah.
My understanding is correct.
Yeah. So this is the flow through layers of the model.
Okay.
Upstairs, and we've done some grouping here. So I will show in more detail. Let me actually see when we're going to get to that. Yeah. So I'm going to give you a lot more detail in just about a slide on the technical side. Yes.
For size for dictionary or for the dictionary?
We did a scan where we trained dictionaries of different sizes, and we, you get some trade-off of just the compute you spend and the amount or the accuracy of the approximation. Like, these are supposed to reconstruct the activations. How well does that happen? The bigger the dictionary, the better it does. Also, the denser it is, the less sparse it is, the better that does, but you pay some price on interpretability at some point. So we did a bunch of sweeps, and then we picked something that seems good enough. There's still a bunch of errors, and I'll show you later how those show up to, mean that we can't explain, a lot of things. Okay, I'm going to go on. So, literally what we do here is train this sparse replacement model. So the basic idea is you have a model, a residual stream, goes through MLPs. We're going to forget about attention right now. And we're going to try to approximate that with these cross-layer transcoders. And so what do I mean by that? So transcoder is something that moves information, so it emulates the MLPs. But the cross-layer is this ensemble of them emulates all the MLPs. There's an architecture called DenseNet from a few years ago, right, where every layer writes to every subsequent layer. And this is like that. So the basic idea is that this ensemble of CLTs have to take in the inputs of all the MLPs stacked together and produce the vector of all of their outputs at once. And a reason to do this is there's no particular reason to think that the atomic units of computation have to live in one layer. If there's two consecutive layers in a deep model, those neurons are almost interchangeable. People have done experiments. You can actually swap the order of transformer layers without damaging performance that much, which means that indexing that hard on the existing layer is maybe unwise. So we just say, okay, these can skip to the end. This ends up making the interpretability easier because sometimes it's just bigram statistics. I see this word, I say that word. That's evident at layer 1, but you have to keep propagating it all the way through to get it out. And so here we could make that be one feature instead of, dozens of features in consecutive layers interacting. And then we just train that optimization. You've got a loss on accuracy and a loss on sparsity. Okay, and so here we replace the neurons with these features. We use just the attention from the base model, so we do not try to explain attention. We just flow through it, but we try to explain what the MLPs are doing. And now, instead of the neurons, which are sort of uninterpretable, like on the left here, we have stuff that makes more sense. On the right, this is a capital feature. And I think it's probably more specific. So this is in, these literal state to capital mappings. Yeah.
Quick explanation as to why overly modeling MLP and not try sorting, say, the entire layer or something?
So I don't know what reasonable. I'd say it's expedient. It loses a lot. I think that from a practical perspective, though, if you want to model the action of the attention layer, or anything that moves information between tokens, then the input would have to be the activations at all of the token positions. Here we only can do one token position at a time, so you can learn something much simpler. I think the learning problem is just like a lot easier. It's also like slightly less clear what the thing to replace the attention layer is that would be interpretable, because it needs to be a system for both transforming information and moving it. And sparsity isn't a good prior there. You've got like a 4 tensor instead of a 2 tensor, and we aren't just sure what the right answer is. So we just did this for now.
Is there potential fear that once you are replacing it, you are imbibing your interpretation of what the relevant features are?
Right. So there's two questions there. One is like, what do you lose by doing a replacement? And the other is like, how much are you leaning on your interpretations of the components you get?
And what is a relevant feature?
Yeah.
That's something that you have to put into the sparse autoencoder, right?
Yeah. Well, so the sparse autoencoder just produces a bunch of these, right? And then, but we do have to interpret what comes out. And so for any particular graph, we have now, the attention is frozen. We have a forward pass with the model sort of through the replacement, where we've got a bunch of the features. We've got these triangles or these diamonds are the errors. So like these don't perfectly reconstruct the base model, so you have to include an error term. And then you can just, track the influence directly. These are just linear maps until you get to the end. There'll be a lot of these active, fewer than there are neurons, but, order hundreds per token. But they don't all matter for the model's output. So then you can sort of go from the output, like Austin here, backwards, and say which features were directly causally relevant for saying Austin, and then which features were causally relevant for those being active, and then which are causally relevant for those being active. And in that way, you get a much smaller thing, something you could actually look at to try to understand why it said this literal thing here. And now but this is all still math, right? Now you have this graph, but if you want to interpret this, then you need to look at, these individual components and see if you can make sense of them. And now you're back to like looking at when was this active in which examples, hoping that's kind of interpretable and the connections between them make any sense. Often these will be in some rough categories. So here's like one Texas feature is like, again, everything's bigger in Texas. Texas is a big state, known for its cowboys and cowgirls. And this other one is about, politics and the judicial system. I'm not saying that like these are like the right way to break apart the network, but they are a way to break apart the network. And if you look at the flow in here, these Texas features feed into the, say, Austin ones, right? There is a path here. And so we sort of will manually group some of these based on, at this point, human interpretation to get a map of what's going on. Yeah.
There's a Zoom question. In CLT architecture, we freeze attention blocks and replace MLPs with transcoders that speak to each other. This is complex, right? So won't this be adding unnecessary interpretability when the underlying connections could be a lot simpler? Also, do you mind repeating the questions so the folks on Zoom can hear?
Yes. The question is, boy, this seems like a lot of extra work. There's a lot of connections between these features, right? They're mediated by attention. And I would agree, but we couldn't find a way of doing less work and have the units be interpretable, right? One way to think about this is the base components of the model aren't that interpretable. So if you want to interpret things as interactions of components, like if you want to use like the great reductionist strategy that's been quite effective at, break organs into, cells and understand how the cells interact, you like have to break it apart in some way. You lose a lot when you do that, but you gain something, which is you can talk about how those parts work. And so this was our best guess today as like parts to study. Okay, so we're still in schematic land here. once we have grouped things to make a graph like this, we can do interventions. So, and these interventions are in the base model, not in our complicated replacement model. They amount to basically adding in vectors that are the feature outputs to another one. And you can see if the perturbations make sense. So if we swap out the Texas by muting those and add in the California features from another prompt, then the model will say Sacramento. If you put in Georgia, it will say Atlanta. If you put in the Byzantine Empire, it will say Constantinople. And so here it's a sign that like we did capture like an abstract thing in a manipulable way, right? You don't put it in and get gibberish, right? And you know, if you're just doing bigram statistics or something, it's not clear how you would get this separability. Okay, so I'm going to get into these three kind of motifs that we see a lot: the abstract representations in a medical context and a multilingual context, parallel processing motifs, which is about arithmetic, some jailbreaks and hallucinations, and then also some elements of planning. Yeah.
These causal graphs when you appear on like a certain scale, or do they appear at like a much smaller point, like stuff?
Yeah. So this approach of like training a replacement model of an analyzing an attribution graph is just math. So you can do whatever you want. And then it's like, are they interpretable? You know, is the question. We do this on a small 18-layer model in one of the papers, which can't do very much and find pretty interpretable things. So I think this works at all scales. I know people who are doing these on like, you know, sort of, now how interesting is it? If your model can't do anything, maybe it's not that interesting, but I think if your model's narrow purpose and small, this would still be useful.
Since you're talking about biology here, and this all seems like something that maybe in a different field has been done to kind of human brains and human brain computations. Do you know, is there any kind of overlap on literature that you're relying on from the real like medicine side of things?
For some inspiration, I think in particular this like, you know, the idea of doing the perturbations, the causal perturbations, and seeing what happens is like a very neuroscience, ontogenetics-y thing to do. Fortunately or unfortunately, like our experimental setup is so much better than theirs. So I think we're now like well past what people can do in neuroscience because we have like one brain and we can study it 1 billion times and we can intervene on everything and measure everything. And they're in there like trying to capture like 0.1% of neurons like at a time resolution 1,000 times worse than the actual activity. So, yeah.
Maybe the other way around.
Yeah.
The doctors can take some.
Yeah. Okay, I want to give you, you know, just. I think it's good to like be able to like actually see some of these. So this is in the paper itself. This is like what we make these cartoons from. Okay, so each of these nodes is like a feature, and an edge is like a causal influence. Here's you know, one whose direct effect on the output is saying Austin mostly, and also some Texas things. It's getting inputs from things related to Texas and from states. And, you know, these, like the art of this is like now you're doing the interpretation. You're like bouncing around, looking at these components, looking at when they're active, looking at what they connect to, and trying to figure out what's going on. And so the cartoons I'll show you are given by grouping sets of these based on common properties. So I said these are say a capital, and you can see that these are different from each other, but they all do involve the models, you know, saying capitals in some context. And so we just sort of piled those on top of each other. And this is what, like, I don't, you know, how many features should you have? I don't know. There's obviously no right answer here, I think. It's not a perfect approximation, but you sort of break it into 30 million pieces, then you put the pieces back together in ways that make a bit of sense, and then you do interventions to check that, like, what you learned is real. Okay, so now...
and emergent properties, and then
maybe this is the biggest difficulty in studying this kind of systems, and clearly LLMs, they kind of start displaying this kind of behavior. So if you start breaking it down, at the same time you end up losing those emergent properties. So how can you balance that, and look at it then not losing all these properties that just emerge when everything is together?
It's a good question. So I think one thing that makes LLMs kind of different is this flow of information from the input to the output, in which it seems like the like latent spaces work at a higher level of representation or complexity as you move through it. And so, like all cells are somehow like the same size, they communicate with each other, but it's all like lateral communication. I think you do see this some in the brain as you go from like, the first light sensitive cells through the visual cortex, where you will get, ultimately like a cell which is sensitive to a particular face. But that comes from things sensitive to less specific things, and ultimately things that like just detect like edges and shapes and those kinds of structures. And so I think as you move through that, you do get these higher levels of abstraction. And so, when I say, okay, there's a feature that seems to correspond to errors in code, this is one of our atomic units, It's like one of the things we're getting when we shatter this is like sensitive to errors in code, but like in a very general way. And so to some extent, I think that like these are built up hierarchically, but that it's just, maybe they're still units. There's another thing that I think we don't have any traction on, which is like if it's doing some like in context like dynamical systems stuff, that I think that will be much harder to understand. And you might need like much larger ensembles of these. Okay. Let's slideshow again. Okay. So here's like a medical exam style differential diagnosis question. 32-year-old female at 30 weeks gestation presents with severe right upper quadrant pain, etc., given this context. If we could only ask for one other symptom, what should it be? Is there a doctor in the house? Does anybody know what the medical condition is here? Yeah, so ask about visual disturbances. And the reason is because this is like, the most likely diagnosis is preeclampsia here, which is a severe complication of pregnancy. And, we're sort of able to trace through by like looking at these features and how they're sort of grouping together and how it flows, that is pulling things from pregnancy, from, that region, the headache, the high blood pressure, the liver tests, to preeclampsia. And then from that to other symptoms of preeclampsia. And then from those, ultimately, there's actually two complete visual disturbances. And, there's a tiny box here showing like, what do we mean by that? This component is also active on training examples discussing, causing vision loss, floaters, in the eye, which is another visual disturbance, lead to loss of vision. The other answer would be proteinuria. And so, it is in the same way thinking about Texas, it's thinking about preeclampsia in some way before like saying what these are. And we can see that intermediate state. It is thinking about other potential diagnoses like biliary system disorders. And if we suppress the preeclampsia, then it will say, instead of visual disturbances with a rationale because this presentation suggests preeclampsia, it will say decreased appetite because this scenario suggests biliary disease, right? And so it is thinking of these options. When you turn one off, then you get like a coherent answer consistent with the other one.
So does this mean the fact that you can intervene so clearly that this is only represented in exactly one location in the network, and that by intervening there, you don't need to intervene in like multiple places?
Well, so no, because three reasons. Okay, the three reasons are: one, this node is a group of them, right? It's a few of these features that are all related to preeclampsia. The second is because it's a cross-layer transcoder; each of them writes to many layers. And then the third is we're creaming it. So here we're turning it off double the amount that it was on. We overcorrect, and you often need to do that to get the full effect, probably because there's redundant mechanisms and stuff. And so I don't think this is the only place it is necessarily, but it's enough. Yeah.
Earlier in your talk, you talked a bit about polysemanticity of neurons. Yeah. So, for example, if you do one of these interventions, like what is it, preeclampsia intervention, right? And let's say I deploy the model for some other problem. Would you expect, what is the distribution of things that this will also hit? If you can sort of give some sense of what would be the not reverse, but what would be other effects?
Yeah, that's a great question. We didn't dig into that as much here. We did a little more with our last paper. I think that you push too hard and the model goes off the rails, like in a big way. Here, this is less for the purpose of shaping model behavior and more for the purpose of validating our hypothesis in this one example. So we were not like, and now let's take a model, we've deleted this everywhere. It's like, no, the model's going through answering this question. Right here, we're turning off this part of its brain, and then we're seeing what happens.
Couple questions on Zoom. One is, in practice, when you trace backwards through these features, do you see a kind of explosion of relevant features as you go earlier in the model, or is it some function of distance from the output?
Yeah, the question is like, as you go backwards through the model, is the number of relevant features go up? Yes. Sometimes you do get convergence. Like the early features, right, might be about a few symptoms or something, and those are quite important. I don't think we've made a good plot to answer that question. I am going to push onwards a little bit, and I'll come back to questions soon.
Gotcha. Just one more. How much are these examples carefully selected or crafted? Does this work for most sentences?
You learn something about most things you try. So I'd say 40% of the prompts that we try, we can see some non-trivial part of what's going on. It's not the whole picture, and it sometimes doesn't work. But it also just takes 60 seconds of user time to kick one of these off, and then you wait, and then it's done, and it comes back, and then you get to learn something about the model, rather than having to construct a whole bunch of a priori hypotheses of what's going on. You just sort of get it. Once you've built the machine, you get it for free, but this doesn't tell you everything. Okay, so here's a question. What language are models thinking in? If there's is it a universal language? Is it English? Is it there's a French Claude and a Chinese Claude inside of Claude, and who gets gated to is kind of depends on the question. And so to answer this, we looked at three sentences, which are the same sentence in three languages. So the opposite of small is big, le contraire de petit est grand, and I can't speak Mandarin. But maybe someone here can say, someone surely is a Mandarin speaker in this room. There's no chance. Thank you. I came to, what's the final character? There you go. I came to see it because we were doing these, this part of the paper, so many times. That, it's the only character I can recognize on the site now. So this is even more cartoony, right, than the last one. I'll get into the more detailed version later. But basically, what we see is at the beginning, there are some of these opposites in specific languages, right? Contraire in French, opposite in English. And the quotation, it's this is an open quote in the language I'm speaking, right? So the quote that follows will probably be in the same language. But then there's this like complex of features about antonyms in many languages, saying large in many languages, smallness in many languages that go together, and then you spit it back out in the language of interest. So the claim is that this is a sort of multilingual core here, where smallness goes with oppositeness to give you largeness, and then largeness plus, this quote is in English, give you the word large. Largeness plus this quote is in French, gives you grand. And we did a bunch of these like kind of patching experiments. You could say instead of the opposite, you could say a synonym of, and just like drop that in. So the same thing in all of them. And now you'll get little or minuscule in French. And so it's sort of like patching in a different state. You can, it's the same feature you're putting in these three places, and you get the same change in behavior later. And we sort of looked at, this does have a big effect with scale. So you can look like how many features overlap between a pair of sentences that are just translations of each other as you move through the model. And at the beginning, it's just the tokens in that language. There's no overlap. Mandarin, when it's tokenized, has nothing in common with English when it's tokenized. So at the beginning and the end, there's nothing. But as you move through the model, you see a pretty large portion of the components that are active are the same, regardless of the language that it was put in. And so this is English-Chinese, French-Chinese, and English-French. This is like a random baseline if the sentences are unrelated, so it's not just like the middle's more common. But when you compare pairs that are translations, this is in a 18-layer model, and this is in our like small production model, Haiku. So this generalization is kind of increasing with scale. Yes?
So it sounds like it can kind of interpret concepts in a multi-lingual way.
Yes.
Have you ever tried doing prompts that are metaphors that are kind of like specific to that language that don't really have translation?
No. If you have some examples of that, I'd love to try it. I think that would be fun.
Some languages understand differently.
Yes.
Passage of time, even feelings.
Yeah.
It's a very interesting question.
Yes. I would be happy for collaboration here. Yes.
So would you say this kind of implies that in the center of the network is the most abstract representation of any given concept? Because
I think I would basically agree with this plot, which is like a little to the right of the center. Yeah, at which point you start to have to figure out what to do with it, because in the end the model has to say a thing.
And then have you seen if you have a harder time finding monosemantic features in the middle of the network where it's very abstract, rather than towards the end where it's very concrete?
If anything, it's actually the opposite. Because if you'll permit me to be philosophical, like the point of a good abstraction is that it applies in many situations. And so in the middle, there should actually be these like common abstractions. It's like dealing with the very particulars of this phrasing or this grammatical scenario that is quite bespoke. And so you would need way more features to unpack it.
Yeah. One more question.
Yes.
Is the same like operation stored redundantly across multiple layers? Like, do you find that, like for example, if you need 5 reasoning steps to get something done for, like in one example, but then in another example, like you need 8 reasoning steps to get something done. Do you redundantly have to store the like follow-up operation on both of those layers?
Yeah, I think this is like a very deep question. So to repeat it for the audience, it's like, do we see redundancy of the same operation in many places? And of course, this kind of, it's like a thing people complain about with these models, right? Which is like, well, if it knows A and it knows B, why can't it do them in a row in its head? And it like might just literally be that A is after B in its head and it have to do a forward pass. And so unless it gets to like think out loud, it literally can't compose those operations. And you can see this quite easily, if you just ask, like, what's the birthday of the father of the star of the movie from 1921, like, it might be able to do all of those, but like it can't actually do all those lookups consecutively. That's like the first thing. So there has to be redundancy, and then we do see this. It was one of the reasons for the crosscoder setup is to try to zip up some of that redundancy. I think one of my favorite plots is not from the so-called biology paper, but is from the sister paper here. Let's find Copenhagen. Okay. So like on the left is if you do this decomposition per layer. And on the right is if you do the cross layer thing. And like basically, it's just like bouncing back around. It's like the Copenhagen is like propagated, it's talking to Denmark, and it's just like happens in like many, many places in the model. They all perform, like small improvements to it. There's another perspective here, which is like the like neural ODE, like gradient flow perspective, where it's like all tiny adjustments in the same direction all the time. And I think the real models are somewhere in between. Okay.
With the overlap of the features here, as the models get larger, you found like if you change like data set very significantly, or also like ordering in parts of the data set, you end up with very different representations.
We haven't done systematic studies of like, data set ordering effect.
Yeah, I guess we're talking about what some machine fails. You mentioned that sometimes the plots are not helpful. I guess I'm curious if you ever have a failure where the attribution graphs look really compelling, but you're not able to compel.
No, I don't. Like we've maybe been lucky. You could have a plot where it's like how compelling was the hypothesis from the attribution graph, and then like how well did it work when you intervened? And the best ones did work, but there are some small failure cases we talk about. Okay, I want to dive into the parallel motif because I think it's actually super interesting, and it's a unique feature of the transformer architecture. Right, it's massively parallel. So to give a really simple example of this. Imagine that you want to add 100 numbers. So the easiest way to do it is you start with one, you add the next to the sum, you add the next to the sum, and you do 100 serial steps. To do that with a transformer, it would need to be 100 layers deep. But there's another thing you can do, which is you could add pairs consecutively in one layer, and then add the pairs of pairs consecutively in the next, and then the pairs of those pairs in the next. And so in log n depth, you could add up the 100 numbers. And given the depth constraints here and the sophistication of what we ask these models to do, it makes sense that they would attempt to do many things at once, pre-compute things you might need, kind of slap them all together. And I'll give you a few examples of this. So if you ask the model to add 36 and 59, it will say 95. If you ask it how it did that, it will say it used the standard carrying algorithm, which is not true. What happens is somewhat more like this. So first it parses out each number into there's some component where it's literally 59, but there's also something for all numbers ending in 9, and something which is that number range, and the same up there. And then you kind of have two streams, one where it's getting the last digit right, and then another on top where it's getting the magnitude right. And even inside the magnitude, there's sort of like a narrow band magnitude and a really wide band magnitude. And then those give you a sort of median band, and then if the sum is in this range and it ends in a 5, then it's actually 95. That narrows it down, and then it gives you the answer. Which is cool. It's not how I would do it. But then again, it wasn't trained by a teacher being here's something to do. It just got whacked every time it got it wrong. Or rewarded every time it got it right, in training. And I don't think we're going to have this next in here, so I want to show you one of my favorite things from the addition section, which is okay, so there's a feature in here. Okay, if anybody here I feel this is a word cell shape rotator test. So for the shape rotators who kind of mathematical thinking. Like, I love this section. So this is the graphs we make to visualize on the arithmetic prompts. This is like, is it active on the prompt A plus B for A and B in 1 to 100? That's a grid, and so vertical lines mean like when the second operand is in a range, it's active. You know, these dots is like, is it a 6 and a 9? You know, so there's a grid. There's bands. You know, a band here is a line x plus y equals constant, right? And so those are where the sum is. So we were looking at this to sort of figure out what these did. But this feature here I really like. So everything in the graph you can hover over, which is kind of neat, and see the feature. And we looked at cases in the data set when this thing was active. Okay? So on this narrow domain, it's active when things ending in 6 get added to things ending in 9, but on the data set, it's active in like all these other cases. So this is like thymus organ fragments, federal proceedings, volume 35. It's like, okay, so in some sense, that has to be a 9 plus a 6 is the volume 35, supposedly, if this interpretation is correct. Here's just like a list of numbers. There's more journals. There's like these coordinates. And so the claim here, if our method is working, is that there's one component that in this context means ends in 6 plus ends in 9, but it's also active in these. So like, this is really working if secretly every one of these examples is the model adding a 6 to a 9, and it's getting to reuse the module for doing that across those examples. And so we dug in, and I couldn't really understand these. So here's one example where this is the token where you know that feature was active, and I just put it in Claude, and I was like, what is this? And it's like, this is a table of astronomical measurements. And it split it out in like a nicely formatted table, and the first 2 columns are the start and end time of an observation period. This is the minutes of an end time that it's predicting. And if you read down the table, the start to end interval is like 38 minutes, 37 minutes, but it creeps up over the course of the experiment to be like just under 39 minutes. And this measurement interval started at a minute with a 6, and the 6 plus the 9 equals ending in a 5. And so the model was just like gutting out, you know, next token predictions for like arbitrary sequences of data it was trained on, and learned in that, you know, of course, to recognize the context what it's supposed to do, but then it needs a bit where it has like the arithmetic table, right? Like 6 plus 9, you just got to look it up. So it has that somewhere, and it's using that same lookup in this like very different context where it needs to add those things. This was another one where it turned out this was a table, and it's predicting this amount, and these are arithmetic sequences. This is, I guess, the total cost that's going up. And so the amount that it's going up by, you know, is this, where you're carrying, that's about 9,000 plus 26,000 is 35,000. This was maybe my favorite, where like, why is it firing here to predict the year? And the answer is because it's volume 36. This journal was founded in, first edition was in 1960, so the 0th would have been in 1959. 9 plus 59 plus 36 is 95. And so it's using the same little bits to do the addition there, right? And so I think when we talk about generalization, like, you know, and abstraction, this was for me like a pretty moving example where I was like, okay, like did learn this little thing, but then using it all over the place. Okay, that's maybe like not the most like mission critical thing in the world, so let's talk about hallucinations. So models, they're great. They'll always answer your question, but sometimes they're wrong, and that is just because of like pre-training. Like they're meant to just predict a plausible next thing. Okay, great. Like, it should say something. If it knows nothing, it should just give a name. If it knows like anything, it should give like a name in the correct language, right? If it knows more, maybe like a common name from the era, or like just some basketball player or whatever, right? And so that's what it's trained to do. And then you're like, you go to fine tuning and you're like, no, like I want you to be an assistant character, not just a generic simulator. And when you simulate the assistant, I want the assistant to say, I don't know, like when the base model certainty is somehow, low. And that's like a big switch to try to make. And so we were curious, like, how does that happen, right? How does this, like, refusal to speculate get fine-tuned in? And then when, why does that fail? And so here's sort of two prompts to get at this. One is, what sport does Michael Jordan play? Answer in one word. It says basketball. The other is, what sport does Michael Batson play? Which is just a person who made up. Answer in one word, and it says, I apologize, I can't find a definitive record of a sports figure named Michael Batson. Okay. Here, these graphs are a little bit different. They've got suppressive edges highlighted here. This is common in neuroscience, like inhibition. And we've drawn some features that aren't active on this prompt, but are on this one, and vice versa. So if they're in gray, it means it's inactive here, but part of the reason it's inactive in particular is it's being suppressed by something that is active. And what we found was sort of this cluster of 4 features in the middle. Michael Jordan, and then we have like a feature for like, it's active when the model recognizes, answers to questions. There's another feature for like unknown names. And then there's a generic feature for like, I can't answer that. And that generic feature, I can't answer, is just fueled by the assistant, which is always on when the model's answering. So it's just like, there's just an always, I don't know, to any question. And then that gets down modulated when it recalls something about a person. So when Michael Jordan is there, that suppresses the unknown name, boosts the known answer. Both of those suppress the can't answer, and that leaves room for the path of actually recalling the answer to come through, and it can say basketball. So that's a cool strategy. But getting back to model depth, there's an interesting problem, which is that like, it might take a while for the model to come up with an answer, but it also would have to like at some point decide to refuse and like get that going. And those are happening in parallel. So you could have a little bit of a mismatch where like it has to decide now whether or not it's going to answer or not, but it hasn't like done all that it can do to get a good answer, right? And so you can get some divergence where for very hard questions, for example, but it still might know, it has to be like, okay, do I think I'm going to get there? And that's like a little bit of a tricky knot, but can't fully self-reflect on the answer before saying it. And so, okay, this is just the intervention. You juice the known answer, and it will hallucinate that Michael Batson plays chess. So this is a fun one. So if you ask for a paper by Andrei Karpathy, formerly of Stanford, it gives a very famous paper that he didn't write. Why is that? Well, it's like, trust me, I've heard of Andrei Karpathy, like from the name. But then there's the part which is trying to like recall the paper. And then it gives that answer, right? But like, and then actually it says that. And then, I think it's covered up here, but then like if you're like, are you sure? It's like, no, I don't really think he wrote that. Because at that point, then the model as an input gets both the person and the paper and can like do calculation earlier in the network again. Now we can juice this. We can suppress the known answer bit, and eventually it will apologize and refuse. There's a fun one in the paper where the model hasn't heard of me. I didn't write that section. Jack wrote that section. And it refuses to speculate about papers I've written. And then if you turn off the like unknown entity and you like give the known answer, then it says I'm famous for inventing the Batson principle, which I hope to one day do. Okay, so there's a lot more we could talk about here. I'm just gonna like speed run these for vibes, and you can like read the paper where we do a lot more. There's a Jailbreaks trying to understand how they work. And, some of it is like you get the model to say something without yet recognizing what it's saying. And then once it's said it, it's kind of like on that track. And it has to balance being coherent verbally with like, I shouldn't say that, and it takes a while for it to cut itself off. And we find that if we suppress punctuation, which would be an appropriate grammatical time to cut yourself off, you can get it to like keep doing more of the jailbreak. And that's a competing mechanism thing, right? There's a part which is recognizing, what am I talking about, what should I do? And then there's a part which is completing it, and they're fighting for who's going to win. Okay.
Do you know if like, in the process of the models planning ahead, it really like gets out open to the examples, or is it very
Cool, let's talk about planning. Yeah, okay, so I think my team would be very disappointed if I didn't talk about this one. So this is a poem, a rhyming couplet written by Claude. He saw a carrot and had to grab it. His hunger was like a starving rabbit. It's like kind of good. So how does it do this? Right, it's like kind of tricky, right? Because to write a rhyming thing, you better end with a word that rhymes, right? But you also need to like have it kind of make semantic sense. And if you wait to the very end, you can back yourself into a corner where there's no next word that would be like metrically correct and rhyme that would make sense. You kind of, logically should be thinking ahead a little bit of like where you're trying to go. And we do see this. So actually, he saw a carrot and had to grab it, new line. And so on that new line token, it's actually, there's a feature for like, things rhyming with it. So this is like after words ending in it or eat in poems, and those feed into rabbit and habit features. And then the rabbit feature is sort of being used to get starving and then ultimately rabbit. And we can suppress these. So if we suppress the rhyming with it thing, we get blabber, grabber, salad bar, and that's because of the ab sound is still there. So it'll just like rhyme with the ab part. If we inject green, it will now write a line ending or rhyming with green, sometimes ending with it. If we put in a rhyme with a different thing, it'll sort of go with E. I don't know if we have it here, but if you just literally suppress the rabbit, it will make something ending in habit when it rhymes. And this was pretty neat. This is like the smoking gun. This is like, oh, okay, like literally, here's a model component. When we look at the data set examples, when this is active, it's literal instances of the word rabbit and bunny. A forward pass on this model, that feature is active on the new line at the end of the sentence. And the model writes a rhyme ending in rabbit. And if we turn this off, then it like doesn't do that anymore. So it's like very definitely thinking about like that is a place to take this. And then that influences the line that's coming out. And so that's a place where even though it's saying one token at a time, it's like has done some planning in some sense. Right? Here's a target destination, and then like writing something to get there. There's equivalent things. There's an incredible thing with unfaithfulness. I'll just say sometimes the model is lying to you. And if you look at how it got to its answer, you can tell. In this case, it's using a hint and working backwards from the hint so that its math answer will agree with you. And you can tell because you can literally see, like, you can see it taking your hint, which is the number 4, working backwards to divide by 5 to give you a 0.8. So when you multiply by 5, you will get 4 and it will agree with you, which is not what you want. What you would want is something like this, where it is only using information from the question to give you the answer to the question. But if you just look at the explanations, they look the same, they look like it's doing math, right? And so here there's a competing thing of like, should I use the hint, which would have made sense in pre-training? It'd let you guess the answer better, and you're rewarded if you say the next token well, so maybe the human's right, and you should use the hint. Should I do the math actually? And these are competing strategies. They're happening kind of at the same time. On the right, this one wins.
So what makes it one strategy or the other? How does that work?
Yeah.
Because they're both available.
Yes.
So how is it coming to this, like, obviously there's more time constraint.
Yes.
Is there some other incentive or motivation driving that?
I think that's the question. So I think in this paper we were able to say like which strategies were used when it got to this answer, but the why I don't think we've really nailed down. I think that to some extent it could be we could look at some of this more carefully. I think in the hallucination case we had a bit of a hint, right? It was like recognizing the entity, so I'm going to do the refusal thing or let it through. Here, though, my strong suspicion is that like it's just doing both, but in a case where it's more confident in one answer, that shouts louder. So it doesn't know what the cosine of this is. So all that's left is following the hint. But I think a big caveat is that like we're not modeling attention at all, and attention is very good at selecting, right? You've got this QK gating, right? That's like a bilinear thing. You can really pick with that, and we're not modeling how those choices are made. So I wouldn't be surprised if for a lot of these, attention is crucially involved in choosing which strategy to use, while the MLPs are heavily involved in executing on those strategies. And in that case, we'd be totally blind to what's going on here.
I've been mulling on this idea for a while. How do we prevent
I mean, that's like $1 billion question. I think if I literally knew the answer to that and it worked really well, I couldn't tell you. I would just like go make Claude the best model in the world because it's always accurate. But I don't know the answer, so I can speculate. I mean, I think like it is in some sense an impossible problem for exactly this reason. And so I think like you could try to train better, have the models be better calibrated on their self-knowledge. You could, I think with the thinking tags, basically, with like the reasoning models is a straightforward way where you do let the model check things. And I think models are much better on reflection than they are on the forward pass, because I think one forward pass is just limited for like these physical reasons. I think as an effective strategy, that might be more the way. Than like not allowing, like how do you keep the creativity? And another possibility is you could make the model dumber somehow. So maybe you could make a model which doesn't hallucinate, but it's just dumber because it uses a bunch more capacity just for like checking itself in the forward pass. And it could be when models are smart enough, people might take that trade-off.
Do you think that the underlying architecture, the transformer architecture?
Yeah, I think that's one of the sins here. It's possible that like with a recurrent thing, you could just give it a few more loops to check stuff. I mean, if you could fully adaptive compute, you could just have it go until it's some level of confident, right? And get variable compute per token, and then sort of bail if it's not. I think there is a tricky thing about hallucination. It's like people think of it as being like a well-defined thing, but like, it's producing like reams of text. Like, which word is the one that went wrong? And there are some very factual questions where that's true, but I think if you think more generally, like what would make a given token a hallucination, it's like a little bit less clear. I want to just see if there's anything. Yeah, okay. So there's nothing else here other than like if you want more, read the stuff. I get this. Probably this ends formally in like 2 or 3 minutes. Is that? Yeah. So I will just be done now. And then people can clap and people can leave if they want, but I will just stay for questions for a while. And I'm happy to like continue doing questions as long as people want. So thank you.